Okay, hello everyone. Welcome to the 22nd session of our discrete diffusion reading group. And today we have Yong'an from NVIDIA who will present his Nemotron-Diffusion Labs paper. And yeah, we're all excited to have you here. Yong'an, take it over.
Yeah, thank you, Shubham. And so hello everyone, this is Yong'an from NVIDIA Research. So today I will introduce our recent work, Nemotron-Labs-Diffusion, which is a tree-mode language model family that can unify autoregressive, diffusion, and self-speculation decoding. And yeah, maybe a bit background about this. Just like for our team, the major goal is to achieve efficient foundation models. And currently in the agentic era, we know that at inference time, the AR decoding is often memory bounded. And this is true for two common use cases. One is for personal agent with a batch size of 1, and one is for the cloud serving with long context. And for these two scenarios, the workload is very easy to be memory bounded. For example, you can see this roofline model here. And for the roofline model, the y-axis is achievable computation, and the x-axis is flops per byte, meaning the number of computation you can perform per memory loading. And you can see for this region, it's compute bounded, meaning yeah, your achievable computation is already saturated with your memory load. But for the personal agent scenario and the cloud serving with long context, they are all falling into this memory bound scenario. You can see there's still a far region to a far gap to mitigate. And to mitigate this issue, for our team, we are trying to address this from two aspects. One is that we are trying to develop more efficient language model architectures, like the hybrid models. For example, NVIDIA just released the Nemotron-3 model family, and which achieve pretty good performance in terms of the intelligence and speed trade-off here. You can see this is the achievable performance of Nemotron-3 Ultra. And yeah, our team also have some other hybrid model designs like Hamba and Nemotron Flash. This is one line of research. And after we squeezing out the redundancy hidden in your model architecture, then the next thing to look into is the modeling paradigm itself. So that's why, in addition to the autoregressive generation, we are also looking to the parallel generation schemes, just like the Nemotron-Labs-Diffusion model we will introduce, which are kind of hybrid AR and diffusion ARM. And why diffusion ARM? Yeah, as mentioned, AR is pretty memory bounded during generation time. But for diffusion, it can make the generation to be closer to the compute bound scenario and achieve 2 to 5x speed up in terms of throughput. And also, another reason, in addition to the speed, is that potentially diffusion ARMs can have higher intelligence. So we know that AR is only learning to modeling left-right orders, but diffusion ARM are learning all permutations. So this is harder to train, harder to learn. But if you can really train it well, it can be a more powerful modeling paradigm for all different kinds of domains. So that's why our vision is that potentially, yeah, given the current internet data, AR is currently we're first scaling better. But when we really run out of all the internet data, which become a kind of data constraint scenario, the diffusion ARM will be a more data efficient learner and achieve higher intelligence. But however, we are not really fully make use of the internet data currently. So that's why our current way to deliver the SOTA diffusion ARMs is that we will do AR to diffusion conversion to stand on the shoulder of the powerful AR models. And as a prior work of our Nemotron-Labs-Diffusion, we actually deliver kind of among the first several blockwise diffusion ARM that can match AR accuracy. So this is one of our ICML accepted paper, which will be presented in Korea soon, which can, this model is converted from the Q13 billion model and can achieve 3x speed up without dropping any accuracy. And this is called efficient DRM. And from efficient DRM, we actually learned something that is important for the success of AR to diffusion conversion. One is about the block attention pattern. So we find that the blockwise attention, just like the block diffusion, is the way to go for AR to diffusion conversion. This can achieve a win-win in accuracy and efficiency. And the second thing is that the left-right prior is very important. So for example, even for a diffusion ARM, even if it is trained with a diffusion objective, but when it is converted from AR models at decoding time, it still have a very huge left-right tendency. For example, you can focus on this. An illustration is shown in this figure. So just like the x-axis is the token position, y-axis is the denoising step, and the highlighted boxes, red boxes, means the token to be really decoded at each denoising step. So you can see that it still have a very clear left-right tendency, although not exactly left-right, but the tendency is very strong. So there's a training and inference time gap, meaning during inference time, you are doing highly left-right decoding, but at training time, you are doing uniform noise masking. This kind of training time gap and limits your achievable accuracy. So that's why in this work, to introduce left-right priors during training time, we will condition the token masking probability on both the time step t and also the position of a token in a block. And after introduce this, this can be achieved by different ways. And one simple way is that for the masking probability formulation, we exert kind of a weight coefficient, higher probability to mask later tokens, and lower probability to mask earlier tokens. This is one simple way to achieve that. And the steepness of this masking probability can be controlled by a hyperparameter here. And generally, with different hyperparameter, this technique can always improve the average accuracy under different accuracy throughput trade-off. So this is second insight. We need to really introduce the linguistic left-right priors and leverage this left-right tendency. And basically also integrating some other tricks, we deliver this efficient DRM, which can achieve kind of comparable accuracy with the AR counterpart, but achieve about 3x throughput. And this is accuracy throughput trade-off. Another benefit of diffusion M we find from the efficient DRM work is that previously for AR models, you need to deliver the whole model family to achieve accuracy throughput trade-off. But for diffusion M, you can easily achieve this trade-off with a single model by tuning the parallelism at inference time. This can be simply achieved by controlling the confidence when you're doing parallel decoding, so that it can naturally form a kind of proto-frontier in terms of accuracy and throughput. And the third promise of this diffusion M is that, since it's not fully causal attention, so it can learn some modeling some bidirectional information from your target domain. And so for some domains like text embedding tasks, it can achieve notably better accuracy than the fully causal AR models. So for example, across these 6 categories of tasks, totally 15 tasks, on average, the diffusion M can achieve about 10% accuracy improvement compared to the AR counterpart. So this is our earlier work, efficient DRM. Basically, it demonstrates for AR to diffusion conversion, we can deliver kind of ideal diffusion M, achieve real speedup while maintaining the accuracy. But actually, this is not sufficient to really justify the switch from autoregressive models to diffusion language models. Because if we really want to deploy diffusion ARMs everywhere, we really need to answer more questions. So we actually propose 3 critical questions for diffusion ARMs. The first one is that although the accuracy can be comparable to AR, but you can see even for the recent release of diffusion JAMA, it still have some gap with the AR model if you do a wide range of tests across different benchmarks. So this makes us ask whether we should really compete diffusion ARMs with AR models in terms of accuracy, or we can try to harmonize them into the same model. This is the first question, the relationship between diffusion ARMs and autoregressive ARMs. And second, although diffusion ARM, they can achieve real device speedup, but we know there exists many multi-token prediction methods that can also achieve parallelism during decoding time. So how will diffusion M compare with such kind of MTP methods? Which one is better? And third, given the high promise of the existing MTP method, do we really have sufficient reason to explore diffusion M's in the long term? Or diffusion decoding, do they really have the potential to support our long-term, to justify our long-term exploration? So this is kind of an innovation for the future of diffusion M's. So we want to answer these 3 questions in our recent work, Nemotron-Labs-Diffusion. And this is a tree-mode language model trying to unify AR-diffusion and self-speculation decoding in the same model. And we want to use this model as a tool, as a bridge, to really study the answer of the 3 research questions. And yeah, we actually released our model on Hugging Face with the tech report, and it was already received 1 million downloads in the past months. And before going to the detail, maybe this GIF is a better illustration of our model. So basically, we released the 3 billion, 8 billion, 14 billion model variants, including instruct and base model and vision language models. And this model can do 3 modes. AR mode is just like from left to right. Diffusion mode is iteratively denoising mask tokens into normal tokens. And self-speculation is a combination of the two, using diffusion to draft and use AR to do verification. And it's kind of a two-forward process to denoise one block. And we already support our model in SG-Long, and the SG-Long implementation is also publicly released, and it can achieve 4x speed up in SG-Long when measured on the GB200 GPUs. Yeah, and before going to answer the 3 research questions, maybe let's see some performance highlight first of this model. And you can see that figure is the accuracy throughput trade-off on an H100 GPU on the batch size one. And ARD is our Nemotron-Labs-Diffusion, the abbreviation. You can see compared to all the AR models listed here, our ARD models all is 3 modes: AR mode, diffusion mode, and self-speculation mode can achieve a better accuracy throughput frontier compared to the AR models. And for inference people, maybe the system throughput versus per user throughput trade-off will be even more important. So this figure measures the achievable throughput under different concurrency, meaning batch sizes. And the top right part will be better. So you can see for the black curve is the AR model's achievable system throughput versus per user throughput trade-off. And the blue curve is the achievable trade-off by the existing MTP method called Eagle3. And for existing MTP method, we can kind of achieve good accuracy, good throughput under low concurrency, meaning small batch sizes. But when the concurrency is high, it actually falls behind AR models. But you can see for our the self-speculation mode of our model, it can achieve a much better trade-off here, much better trade-off under low concurrency. And under high concurrency scenario, you can see it will fall behind AR under batch size 128. And for our model, because it's 3 mode, meaning it can directly switch to AR if AR perform better there. So actually, the achievable performance of our model is kind of the proto frontier here. Yeah, this is some performance highlight. Then we use this model to actually our major goal is to study the answers to the 3 research questions. The first one is that what's the relationship between AR and diffusion? And our hypothesis is that actually these 2 losses can be potentially complementary instead of competing with each other. The reason is that, we know for AR models, they are already implicitly predicting the future. Just like for like a paper from Apple that your ARMs already implicitly know the future. So when you're predicting the first token in the AR mode, it already needs to plan for the future for a while, right? So that you can ensure the fidelity of your generation. But this is just like something implicitly learned instead of explicitly trained during your training process. And that's something AR language models misses, that is explicit future planning, training loss. And for diffusion, they are good at planning the future because during training process, you will already append a block of mask tokens and explicitly train to predict the future. But what diffusion model misses is the left-right linguistic priors. They don't know the relative importance across different permutations. They're trying to jointly optimize all the permutations together without any focus. So that's what AR losses can bring it. So that's why our vision is that these 2 losses actually can complement each other and achieve a win-win in the future prediction ability and also the left-right linguistic priors. So that's why our model do a joint training of both. We use the weight coefficient to combine both losses. And we empirically find that the best way to combine the 2 losses is that make the absolute magnitude of the 2 losses to be comparable. And because for diffusion loss, it's generally 2 to 3 times larger than the AR losses. So it seems that empirically picking a coefficient that align the magnitude of the diffusion loss with the error loss can achieve the best result. So we thought, as shown in a later ablation study, this kind of coefficient work well in all our experiments. So we adopt this setting across all our base model training, instrument model SFT, and also the vision language model training stage. And how we train this loss efficiently is that we will try to do that in one forward pass. This is very similar to block diffusion. We achieve this through a specialized attention mask. Basically, given the original input, we will do add noise to the clean input to create the noisy counterpart and concatenate it with the original clean version. And you can see the diffusion loss is predicted over the mask tokens in the noisy part, and error loss is predicted on the clean part. And the interaction across these two parts is achieved through this specialized attention pattern. This is very similar to the block diffusion attention pattern. The only difference is that for the clean context part, we replace the block-wise attention pattern with this causal attention pattern. Yeah, and let's see some results. Let's first focus on the diffusion accuracy. The baseline is a vanilla block-wise attention pattern. On average, this is during pre-training, we average over 6 coding and math tasks. And we actually, in addition to the error loss, we also progressively add other techniques here, like global loss averaging to treat all tokens equally across all samples in a batch. And this is kind of, compared to the vanilla baseline, this is just like the difference between the DAPO method. I mean, in the GRPO domain, that's the DAPO method versus the vanilla GRPO. The global loss averaging is similar to the difference there. And for more details, you can refer to our paper. And another trick is that we will ensure different data samples to use different masking ratios, which we find that this can achieve better performance than assign the same masking ratio across all samples, across all DP ranks, data parallel ranks. And also we find that another insight here is that we find that only a sufficiently trained AR, they can do better AR to diffusion conversion, meaning your AR likelihood should be already kind of calibrated, accurate enough. Then we can do a successful AR to diffusion conversion. So that's why we do two-stage training. First, fine-tune our model with an AR objective using our data distribution, and then apply the joint training with both AR and diffusion losses. And finally, adding the error losses here, you can see that among all these techniques, when combine the error loss, this can achieve the most significant improvement. Yeah, this actually very interesting, indicate that the error loss, thanks to the introduced linguistic prior, the left-right prior, it can significantly boost the the diffusion accuracy. So it seems that if we want to ensure good diffusion performance, we always want to maintain the AR ability of the model. And also, you can see in this table, we just like do an ablation of the weight coefficient, the alpha, shown in the previous equation. And generally, when we vary in different alpha here, you can see both AR and diffusion accuracy, they will peak at the same alpha. So it seems that this is not a zero-sum trade-off between AR and diffusion. They will actually peak at the same time. And also, the two objectives will rise and fall together. So this indicates that they are complementary instead of competing for capacity in the same model. Okay, so we also do another experiment that is kind of an inverse setting, meaning we already see AR loss improve diffusion loss a lot. What about the impact of diffusion loss to the AR accuracy? So we try to answer this question in two settings. One is base model pre-training, one is instruct model SFT. So you can see for these two tables, basically, our baseline is that we will train with only AR loss. And on top of exactly the same setting, we only introduce the diffusion loss on top of the setting with all everything, meaning the training data, learning rate, all every setting the same. So you can see for base model and the SFT setting, both of them, after introducing the diffusion loss, they can maintain the AR accuracy across all benchmarks and even slightly boost it by up to, on average, 0.4%. So it seems that diffusion loss can maintain or even boost the AR loss as well. So this kind of answered the question the relationship between AR and diffusion objectives. So the two, we find that when properly trained with the correct scheme, they can be complementary instead of competing for capacity. So our vision is that we should always keep the two losses for the same model if we want to, even if we want to emphasize parallel decoding. Okay, this is the our answer to the first question. And to answer the comparison with existing MTP methods, so then we need to dive more into the supported inference modes of our model. So actually, we should never directly compete diffusion with MTP, because all MTP methods, they will have a verification stage. But for diffusion, naively, they are only doing drafting, no verification. So the two are not kind of competitors. So we should actually, what we really should compete is the self-speculation mode of our model and MTP. And more specifically, after training our model with AR and diffusion loss, in addition to the AR mode and the diffusion mode at inference time, naturally, our model can do the third mode, that is speculation. Meaning you can use diffusion mode to do draft and use the AR mode to do verification. And all the two models, they can actually share the same set of weights. And yeah, this will naturally emerge after the joint AR and diffusion training, another benefit of using two losses. And also the KV cache can be kind of reused when you do the verification, meaning after you verify the draft from the diffusion mode until the first mismatch token, all the match token before their KV cache can be cached and reused. So so in the next iteration for the diffusion draft, they can directly start from the next token. No need to kind of recompute the KV cache. So this is the three mode of our model, but certainly you can do some kind of further variations on top of it. For example, on top of the diffusion mode, usually people will do confidence-based sampling, but we know confidence-based sampling is kind of a implicit post-training signal. It is never optimized during training. So what we can do is that we can do a very simple training to train a sampler to replace the confidence-based sampling. So the sampler can be super simple, meaning you can directly input the confidence scores and also the embeddings of the last layer to the sampler and let it decide whether to accept or reject the proposal by the diffusion mode at this position. And this can be trained by just collect some denoising trajectories from your trained model, and then do a kind of BCE loss, just like binary decision whether to accept or reject based on the trajectory, denoising trajectory. So yeah, and just using this very simple scheme, the sampler can achieve very decent performance. For example, if we see the accuracy and TPS, means decoding tokens per forward, you can see the green curve is confidence-based sampling, and the orange curve is the sampling with the sampler. It can achieve much better accuracy TPF trade-off, especially under some aggressive parallel decoding scenarios like here. Yeah, if you do very aggressive decoding, confidence-based sampling will drop significantly, but for the samplers, it can much better maintain the accuracy. So there are also some relevant works from NVIDIA. From our colleagues Jian Tao's team, they have a work called D-Ultra, which kind of have a better objective to train the sampler. Basically, they use outcome reward to train the sampler instead of some imitation learning. And the D-Ultra work really achieve even better sampling performance. So yeah, my point here is that instead of confidence-based sampling, you can certainly train better samplers to push the frontier achieved by the diffusion mode. And also for the linear, for the speculation mode, self-speculation, we can also further enhance it because our model during training, they never explicitly learn for the draft and the verification process. So the simplest thing to do is that after training this model, you fix it and train LoRa to explicitly train for the draft and the verification process. And the loss can be simple, just like you during the draft process, you train a LoRa there. You try to ensure the prediction of the draft mode can align with the AR mode. And there are some existing loss for that. For example, LK loss. This is not KL. This is actually a lot. LK loss is a loss for the speculative decoding. try to maximize alignment. And we find that after tuning this LoRa, you can see, for example, if you focus on the HB model, without this LoRa tuning, our model out of the box can achieve, can decode 4.5 tokens per forward. But if you tune this LoRa with a very low training cost, you can achieve, further improve the token per forward by 30%. Yeah, it's kind of easy fish to achieve that. And in addition to the self-speculation, we can further enhance it. For example, here, we only do one draft and one verification. But we can make this thing more complex. So one bottleneck of this process is that if your prediction and earlier, I mean, if finally the aligned token is only a few, only the first or the first two tokens are accepted, then you kind of, the achievable acceptance length or the TPF will be limited. So a variant to improve this bottleneck is that we can always consider the worst case, meaning we always ensure that the future is considered for every possible accepted position. So this is called quadratic self-speculation. More specifically, when you already have a draft like this, we will always, during the verification process, we will do the drafting process simultaneously. We will consider the worst case, meaning for each possible accepted position, we will append a block of tokens there and do drafting for all of them, so that this will be a speculation of all the potential futures for any accepted position there. And during the verification process, if you find that, for example, this is the largest meshed position with the AR mode, then you can see you already drafted the future for it. Yeah, so it kind of, this mode achieve decoding, achieve drafting and verification in the same forward process. So you don't really need to forward to do draft and verification. So the cost of this process is that instead of having a linear complexity to do the draft, you can see the cost is quadratic here, meaning the per forward cost will be super high. So this mode will not be achieve good real device efficiency if you have a very large batch sizes, because per forward cost is super high. But under some low concurrency scenario like batch size 1, this mode still have high promise. For example, it can boost the achievable token per forward from the 4.5 to 6.4 on our HB model. Yeah, it can achieve better speed up under this batch size 1 scenario. But the cost is that, super high computational cost per forward, and also you need a special attention mask to achieve this decoding behavior, to achieve this decoding pattern. And this is usually achieved by flex attention. And currently our flex attention implementation, maybe the kernel is not so good, so the real device speedup cannot match the achievable theoretical token per forward. So that's why throughout our major comparison with the MTP method, we still use the previous linear self-speculation as our default mode. But certainly this quadratic coding is promising, but needs kind of better infra support and also some algorithm optimization. For example, you don't need to predict all the positions here. You can just predict at the most promising position, so you can prune some mask here. Yeah, these are some potential algorithm optimizations there. Okay, so yeah, among all these modes, linear self-speculation is the most promising decoding mode, achieve the highest token per forward. Let's compare it with the existing multi-token prediction method. Okay, so we pick the Eagle 3 as our baseline, which is one of the most popular multi-token prediction method. You can see here, this figure is as mentioned, this is the system throughput versus per user throughput trade-off. The top right is the best. And the other three figures, they are under the batch size 1 evaluation, and they are across different devices, RTX Pro 6000, GP200 GPU, and also your personal personal PC, the DGX Spark, and all this.
Sorry, one clarifying question about the figure on the left-hand side. What is the average context length? Is it from Speedbench or?
Oh, good point. Speedbench.
Oh, okay.
So the context is not so long. It's not long context.
Like about 1,000-ish. Okay, cool. Sounds good.
Yeah. As Shubham mentioned, all these benchmarks are measured on SpeedBench, so which is a kind of recent speculative decoding benchmark from NVIDIA. And covers different domains: math, coding, creative writing. So okay, go back to these figures. You can see for this batch 1 evaluation, we include both. Sorry, let me turn on the laser. The black part is the AR accuracy, the AR throughput, and the green one is our achieved performance for our model, linear self-speculation mode. And we will talk more about the red one later. And the blue one is the Eagle 3 method. And you can see there are 2 bars for each of them. So this means different precision. For example, for the RTX device, it will be FP8 versus int4. And there's also FP8 versus int4 for the DJI Spark device. For GB200, we only show the FP8 performance. So generally, you can see that across all these devices, our linear self-speculation can achieve notable better improvement over the AR method and also the MTP methods like Eagle 3. For example, over AR on the GB200, with our optimized kernel, we can achieve about 4x speedup over AR and about 2.5x speedup over the Eagle 3 method. And also, as mentioned in this system throughput per user throughput trade-off, we can push forward the frontier, and especially under high concurrency scenarios, MTP method will fall behind significantly over AR. But for our model, we can simply switch to AR under these cases and only use self-speculation under some low concurrency scenarios. So
just a quick question. So I'm looking at the speed up for the linear SS mode to be less than let's say 8x, right? But when I look at the paper, the block size is 64. So I was trying to reconcile these 2 things. Like if the actual speed up is much less than the block size, would it be reasonable to use, let's say, a smaller block size, or is a big block size necessary for the?
That's a nice question. You can see for this figure, actually, we explicitly consider this. You can see for our curve here, under low concurrency scenarios, it's totally fine to use larger block size. But under the high concurrency scenario, as you mentioned, if larger block size will result in higher per forward cost, right? So that's why under high concurrency scenario, you can switch to use lower block sizes. Like this point is measured with block size 8. We actually annotate this in the figure here. So yeah, this is certainly a trade-off. And in the extreme case, like super high concurrency, we want to use block size 1, meaning use AR mode.
I see. I guess I'm also trying to understand, like, even if you use a larger block size, like, you can't actually verify, let's say, so out of the 64 tokens, you can't actually verify, let's say, 15 tokens, right? Like, that would be, that seemed to be very big.
Oh, yeah. I got a point. I think you mean just like, for example, you already dropped a large block, but based on some confidence score or other indicators, you can actually only validate part of them, right?
Yeah.
Would only validate the promising part. Yes, we actually have one idea very similar to this. Actually, we are trying. Yeah, that's a good point. We can do this, and we also have an idea that is doing simultaneous draft and verification, kind of a pruned version of the title, using similar idea there, based on some indicators to see which would be the potential kind of acceptance position, and only draft from there. Based on similar ideas, following similar insight here. Yeah, but that's a good point. Yeah. Okay, then this kind of answers the second question, meaning diffusion AM is not a competitor for MTP. Actually, the true modes should be compete with MTP is the self-speculation mode, and with our recipe, it actually can achieve much more promising result than the existing MTP methods. Okay, then given that linear self-speculation achieves such good performance, and it seems that currently diffusion cannot achieve this TPF. Diffusion seems to be only useful during training process to help us reach this self-speculation during inference time. So then do we really have sufficient reason to do diffusion style decoding at inference time in the future? Should we only use self-regulation in the future? So this is our third question. So what would be the real promise of the diffusion mode decoding? Do we have sufficient reason to justify its long-term exploration? So so to answer this, we're trying to do a speed of light analysis, meaning we're trying to identify the upper bound achievable speed up by the diffusion mode. So if the highest theoretical speedup of the diffusion mode is still promising, then we have kind of sufficient reason to justify the long-term exploration of it. And to achieve the SOL, meaning speed of light, the upper bound of the diffusion mode, we actually have an algorithm to deliver the SOL solution for the diffusion mode. And maybe an easy way to illustrate that is that we will first have a ground truth. The ground truth is defined to be the denoising trajectory when you decode only one token every time using the confidence as an indicator. So when you decode one token at a time, finally you reach a trajectory. This will be the best trajectory can be achieved by the diffusion mode. So we use that as a SOL and trying to see what is the maximum number of tokens to be accepted at each denoising step that can ensure that after accepting this amount of tokens at this denoising step, we can still finally reach the ground truth. So this is the way we define the SOL, meaning the maximal parallelism can be achievable, but you can still ensure exactly recovering the original ground truth. And and you can see to identify the SOL solution, actually we need ground truth here as a reference, meaning this one is not practically achievable yet. This can only serve as an upper bound. But if in the future we can have a better sampler, a better metric to guide your diffusion sampling process, we can potentially reach this upper bound. Yeah, this is a note that this is only a theoretically achievable performance for now. And then let's see some comparison between the SOL performance, the theoretical SOL performance, with the currently practically achievable linear self-speculation performance. So we show two things here. One is the acceptance rate. One is the token per forward. For diffusion SOL, it's actually the two metrics is pretty similar, meaning because when you draft it, we by default accept it. But for linear speculation, the TPF is actually is acceptance rate divided by 2. The reason is that after you accept it, after you draft it, you still need a verification process, meaning you need to double the computational cost to finally accept this amount of tokens. So the TPF is kind of halved over the acceptance rate for the self-speculation mode. Okay, let's first focus on the acceptance rate. You can see the red part is the theoretical SOL performance, and the green part is the self-speculation. The SOL actually, it's higher than the self-speculation, but we can see the gap is super close now. It seems that the linear speculation, if we do not consider the verification cost, it can already achieve pretty similar acceptance rate with the diffusion mode. So this is very interesting because this indicates that the verification process itself can be used as a sampler. This is sampling process to help you sample a kind of very accurate prefix. Although this sampler is super costly, because it's almost the same as your full model forward draft cost. But this can already achieve very accurate sampling process. So then the thing is that if we have in the future, one promising direction is we want to have a low cost sampler that can achieve a very similar performance, very similar effect as the verification process, but with a much lower cost. So you can see if you focus on the TPF, the diffusion SL will be much better. Linear SS suffer from the verification cost, much lower TPF, and diffusion SOL can achieve about 1.7 to 1.x further speed up over the linear speculation. So this indicates that, diffusion mode will still have high potential to be explored. For example, deliver a better sampler. This can achieve 1.7x speed up out of box without any further training algorithms improvement. It can directly achieve 1.7x over the linear speculation mode. Okay, this is third question we want to answer. diffusion mode still have kind of promise for long-term exploration. And combining all these insights, we actually deliver our final model. And we have different model sizes, and this is an example for our HB model. You can see this is average accuracy and also the achievable token per forward. Basically, we can achieve we can decode 6 tokens per forward. We're ensuring higher accuracy than the Q13 HB model. And for coding and math domain, this is even more significant. And for our other model sizes, like the 3 billion and 4 billion, the trend is very similar. Just like for our 14 billion model, also 6x tokens per forward. We also train our HB model into a vision language model, and it is the current best diffusion VRM across all existing diffusion VRMs, public diffusion VRMs. And it can be especially powerful on some long COT benchmarks, like for I think it's MMU Pro. It can achieve about 7.5x speed up on questions that require answers more than 200 tokens. Yeah, this is all about our model family, and here are some key takeaways of our Nemotron-Labs-Diffusion. First, AR and diffusion objects, they are complementary and mutually beneficial if we adopt the correct training mechanism. Second, tree model generation naturally emerges after the joint AR and diffusion training, which is for free and can outperform the existing MTP methods for efficient deployment, especially for personal agent with low concurrency. And self-speculation is currently the most efficient mode, especially linear self-speculation. But the quadratic self-speculation can also have high promise if we have better infra and kind of improved algorithms to reduce the per forward cost. And the diffusion mode still have 1.x additional speedup over the linear self-speculation, and to really achieve that, we need better sampler. So yeah, welcome to try our model on our Hugging Face, which already have 1 million download. And also welcome to look into other diffusion M works from our big team, FastDM2, Tider, and also recent FastDVRM. Yeah, thank you. That's all for my talk.
Yeah, that's great. Should we take questions, or do people have questions, or should I go first? Okay, I'll go first then. Okay, so let's go to the very first slide that you had. Like it was on personal agents and cloud agents, right? Like maybe second or third slide. Yeah. Okay, so here. Okay, so I think So what is a personal agent? You mean like I mean I do understand, like there are companies like Cerebras as well, like their entire business model is based on like accelerating batch size one inference, right? So when you say personal agent, is it like somebody who is just has a lot of GPUs and they just want to optimize the speed just for their task? Is that what you mean? Or like on device, maybe like using an Apple Watch, I'm doing some AI stuff on it, like the batch is always one, right? Is that the examples, or?
These are all good examples, and you can see recently Jensen announced the RTX AI PC, right? And also we have DGX Spark. All these devices, they are kind of representative examples for personal PC. And the model, the vision is that this is just like a personal PC. It's just like you put it near your feet, and your personal agent, like your coding agent or some web search or shopping, all these kind of agents just run locally on these local AI PCs. And we want it to be pretty fast on this batch size one scenario, right? There's no other request, just one request per time.
Yeah, I think right. I mean, because I think like when we say like diffusion is faster than AR, like it is in such very specific scenarios, right? Like when your batch size is one, or when your context length, like that also limits how much speed up we can get with diffusion. So okay, and the other question would be like this cloud serving. Like, what exactly is cloud serving? Like I don't know, everything is in cloud, right? Like, what are we saying?
Good point. So Yeah, this is just I simply mean that cloud serving that like you have multiple requests, just like GPT. They are serving multiple users, multiple requests come at the same time, right?
Yeah.
And if it is not long context, then as shown in my figure, yeah, like this figure, the AR will be kind of better, right? Because in this scenario, it's already compute bounded. I mean, this scenario under not that long context.
Yeah.
But
Yeah.
for especially in the agentic era, the context super long, right? For super long context, the KV cache loading will become the bottleneck, not the model weight loading itself. It will become kind of memory bounded again. So in these cases, you may want to further move it to the compute bound by parallel computation.
Oh, I see. So yeah, I was running a bunch of benchmarking experiments, like with all, let's say, Nemotron-Diffusion, diffusion Gemma. Like what I observed was as you increase the context. So this figure that I'm looking at right now on the right, the average context length was close to 800 or 1,000 tokens, right? But as you increase your context length, I think the curve for the green curve will start moving to left to the point that it's slower than the AR model, right? And I think I did that for a context length of 100,000. I definitely did not try it. So are you saying if so the green curve moves to left as we increase the context length, but after a certain point it starts moving to right? Like is that what you're saying?
Yeah, the green curve will move up if you have a super long context. Meaning if you increase your context length, kind of under super high concurrency, still the diffusion mode will still be better. Yeah.
So I think if you're increasing the context length, your concurrency decreases, right? So what I was trying to say is, let's say to give you some concrete numbers, maybe like with a context length of 100,000, maybe Nemotron diffusion would get a throughput of, let's say, or diffusion Gemma for that matter, right? Like my comments are not specific to Nemotron diffusion, but like any diffusion model, right? So let's say that diffusion model gets, with a context length of 1,000, gets a throughput of 1,000 tokens per second, right? But as you increase the context length to, let's say, 100,000 tokens, that throughput will drop to 100 tokens per second, but the AR would suffer as much. But if I were to, so my point is that with a context length of 100,000, maybe the AR model is faster than the diffusion model. But are you saying if I increase the context length to, let's say, 200,000 or 500,000, a million, right? The diffusion will be faster than the AR model, or like,
yes, that's my point. Yeah, when you really increase your maybe 100K is not sufficient. Maybe you can try 500K, 1 million. Under this scenario, the KV cache loading will become the bottleneck. In this time, you want to increase your kind of computation arithmetic intensity. So in this case, parallel decoding will be even better. So you can refer to a better figure. There's a paper called Magic Decode, and they have exactly a figure like this. They are trying to say speculative decoding also can serve for high concurrency scenarios when the KV cache become the bottleneck. They have a kind of more practical figure there, a real figure there. Yeah.
I see. Let me share that.
Yeah, from CMU, the paper. Yeah.
Paper on chat so that other people can see. I see. But also, like, what if your model has some, I don't know, some slighted attention, or the truncate the attention at, I don't know, 100,000 tokens, then it won't be an issue, right? Like if you're not attending to the full
like sliding window, truncate your context length.
Yeah, if you just like have some
yeah.
I wonder.
Then you need our model. Try to switch the mode under high concurrency scenario. Switch back to AR.
Yeah, I see.
Yeah.
Okay. All right. My other questions would be like regarding the training, right? So, I mean, in the paper you said so there was mention of Mistral. Like, is it like you're using the architecture of Mistral, or are you pre-training from a Mistral checkpoint?
Yeah, both. We are using Mistral architecture and pre-training from the Mistral checkpoint. The reason is that we intentionally skip human models because we actually want to demonstrate. Actually, we want to demonstrate the pre-training, whole pre-training. So we don't want to stand on the shoulder of a well pre-trained model. But because we still want to save some training cost, so that's why we start from a weak checkpoint. That is Mistral's model. Yeah.
Okay, so all right, so you start from that checkpoint, and in the paper you say you train the model in the AR mode for 1 trillion tokens,
Yes.
right? Or okay,
Yes.
okay, and then you do diffusion training for 0.3 trillion tokens, right? Or
Yeah, 0.3 trillion tokens.
okay, so and when you compare your method in terms of accuracy with respect to the AR model, it's with the checkpoint that was trained for 1 trillion token, right? Like the ministerial layer checkpoint that was trained for 1 trillion token, is that correct?
Yeah.
And when you fine tune the diffusion model on extra data, like is it the same? Is it from the same distribution, or like do you use a different subset, or like a
The same
different?
distribution.
Oh,
Same
so is it,
distribution.
is it like you have this 1 trillion, let's say whatever, like training split, right? Do you use the first 300 trillion, so first 300 billion tokens to for the diffusion conversion, or like it's a new data that you?
Let me clarify. We have 6 trillion tokens, and from the same distribution, randomly sampled, the first 1 trillion for the AR mode, and another 300 billion, for the diffusion training. And when we compare to AR, actually you mean the AR versus AR plus diffusion results, right? We are training on the same set of tokens, meaning for the AR, we further also trained for 300 billion tokens on the same set of 300 billion tokens. So it's all the same data.
I see. Yeah. No, okay, that's very helpful to know.
Yeah.
And so my other question would be about the sampler. You mentioned, I think I missed that part where you retrain on a sampler. There's some mention of PCA as well. Could you please explain this to me a bit more? Like, maybe this
great.
part.
Yeah, actually, this figure is a little bit overcooking. Actually, we even don't need PCA. So our point that the sampler can be trained in a super easy way. So basically, after finish the model training, we can use confidence-based sampling to do sampling, and also we can just train a sampler to do accept or reject. So it will have a binary prediction whether to accept or reject the current proposal from the diffusion mode. And the input to the model, actually, we tried many variants, but this actually can be very simple. It's just simply we can simply input the confidence scores and the top 3 tokens embeddings, and or we can just like to save some efficiency. We can just do a PCA on the embeddings. Yeah. So, but this is not necessary. Basically, I think all kind of input can work similarly well. So this sample we actually didn't do too much study. We found that it can directly work out of the box if you try to train it on a small portion of denoising trajectories offline collected.
Oh, yeah, that part I was not fully, I didn't quite fully understand when you said train it on denoising trajectories, right? So the sampler, is it like 4-layer transformer as you mentioned at the bottom?
Yeah, it's we actually have different variants. It can be 2-layer or 4-layer transformer, which can be super simple. Yeah.
Okay.
And the training of the input is just like you can do any feature engineering you want from the final model output. And the training is that we will first collect a denoising trajectory, meaning directly use the confidence based mode of our model to do kind of 1 token per step denoising to collect the trajectory. We view it as kind of a ground truth. And using this trajectory, we can use to train the sampler to see, okay, given the current input, whether you should accept or reject each token at the position to exactly recover the trajectory we offline collected. Yeah, this can be a short training process.
I see.
Actually, I think Diatro, another paper from Jiantao's team is doing that in a better way, just like using outcome reward instead of this hard imitation learning.
I see. All right. Makes sense. Yeah. Oh, sorry. One other question about training the model. Did you try using some annealing techniques for the block size, where you or like not annealing, but like did you try increasing the block size?
Great question. Yeah, that's great. Actually, I find that when we have error loss there, annually the block size annually no more make a difference. So we didn't use any annuling there.
Okay.
Yeah.
Okay.
Well, I find that when error loss is there, it kind of I think the annuling kind of want to ensure a smooth transition, right, from kind of higher linguistic left-right prior in the beginning from smaller block size to larger block size, right? But when we have error loss, I find this makes no difference. Yeah.
Oh, okay. Do you have these ablation experiments in the paper, or like these experiments were
no, we
or no?
didn't show that in the paper, but yeah, we do that in our when develop this model. Yeah.
I see. Yeah, cool.
But one thing to notice is that a written paper from Dream team, you may also notice that called Dream Reasoner or something like this. I think block size annealing might be more important for reasoning model training, because we are training reasoning agentic models now for this model, and we are trying the block annealing again there, because that might make a larger difference according to the Dream Reasoner paper.
Could you share the paper or just
yeah,
check
sure.
out?
Sure. I will share it. Yeah.
So you're saying like this block size annealing helps with when you're training reasoning models, or like, but like this is
Yes.
also reason, right? Like, what am I going to say?
Yes, exactly. Because we do find that we haven't fully tried that on our model reasoning training process yet, but we do find that for reasoning process, it's more likely to decode conditionally dependent tokens together. Meaning, if you do more aggressive parallelism, the accuracy will drop more significantly than pure instruct models. So that's why we see the Dream Reasoner paper. Maybe the block size annealing might be a kind of remedy for that. Yeah.
Okay. Yeah. No, I think you've answered pretty much all my questions. I don't have any other questions unless other people have any. Yeah. Okay. Seems like nobody has any other questions, so I guess we can end the talk now, or well, okay. All right.
Yeah,
Thank you so much, everyone. It was really a pleasure having you present your work. And yeah, I guess we'll see each other in Korea.